Professor, I think you're muted.
So I'm not muted anymore. And that sounds good. Okay, thank you. All right, so we're about 23 or so strong at this point in time. Let me just get this on my shirt here, just in case I lose it. All right, so as I said, we're in a different location. As you can see that I'm actually, my background has changed. And I'll try to make it in this room for a little while. Let's see, I have to unplug some things because otherwise they're going to be in my way. This is where I usually record my music, and I was basically going to do the class from here for a while. So let me just say a couple of things. I guess logistically speaking, there is a homework deadline that's coming up after this weekend, and we're not going to stretch the time. There's a lot of time between now and then, unless you have special permission through DSS to do your homework, and submit it at a later time. You're all bound by the deadline. That means we're not going to have an extension. So, please do not plan on looking for an extension when Friday comes, next Friday, that is. So do your best. Now, I'm going to talk a little bit about the homework assignment today. And so hopefully that'll give you a little bit of a direction. And with that, you can maybe have a quicker start. Now, let us see what, the homework is. I don't have it in front of me. I'll just pull it up and I can tell you what the homework actually intended. And that way we could just kind of go forward with it. There we go. Assignment number 1. You won't see this at the moment. The reason that you won't see it because I'm not really sharing anything with you right now. If anything, I will share my iPad as we've done this before, but I just like to take a look at the problem myself as we speak. Now, let me go ahead and bring up my iPad so that I can tell you a little bit more about this homework assignment. So let's see, to do that, I got to get back to this Zoom business. And here's share screen. And that means I'm going to basically click on this iPhone business. I'll say share. With that, now I'm going to have a couple of other little surgeries here. That should really bring me back on. Okay, there you go. You see my iPad right there. You'll see it, more, bright or brighter. And so here's the deal. I guess some people would probably be asking for permission to get in. I'm looking at the homework assignment while I'm also tracking this iPad view. So let's just read this problem in slow motion and see if I could just give you any hints as to what it is that you should do. Please do pay attention because, like you may send me an email. It may take me a while to respond. So it's important for you to, I think, to be in class for these kinds of reasons and also, take notes while I'm telling you things. So here is a hypothetical processor and it has 18 instructions. Now, our VEST machine had only 8. So this one has 18 instructions. That means it has more instructions than 8. What that means is that if you were to code these instructions, you're going to need most likely more bits. The first thing that you have to think that you're going to need more bits to represent these 18 instructions. Now, since 18 is stuck between 16 and 32, you probably figured by now that you're going to need 5 bits to represent all these 8 instructions. Okay. So I just answered part A.
I have a question. So 5 bits, you mean like 5 bits is that the number that goes 2 to the n? Is that the n number? Is that the beats?
Yeah, 5 is 5, like not 6 or not 7. Like when we had 8 instructions, we had 2 raised to 3. That would give you 8. So when you raise this to 2 to 5, you get 32. And 32 is greater than 18.
So when it says how many beats? That's the n number. N is the beats that
I just gave you the answer, Yekta.
I just wanted to make sure that.
I don't think you want to make sure at this point.
But no, I don't. I wanna know when the question asks about the beats, like how many beats is that the n?
What is a bit, by the way? Let me turn the table on you. What's a bit? What's a bit? Anybody? Not just Yekta. I don't want to pick on her too much. What is a bit? Anybody?
It can either be a 1 or a 0.
Okay. So it's a piece of information that can either be 1 or 0. That's what a bit is. Okay. How many bits do you need to represent 18 things? Now you think about this.
Well, we
I
have.
already gave the answer for you, but you think about this more.
So we need,
Okay.
we need it to be more than 18. So it's either 16 or 32 or 64 or 128. And in order to
Just
get
think
there,
about the rest of it on your own.
okay.
Yeah, I'm not answering all the questions. Remember, this is not like to do the homework for you. I'm giving you hints, so you think about those, all right? So I'm not going to tell you yes or no on those questions. I want you to think about them. All right, so I said that I just answered this question also. All right, let's continue now a little bit. Let's now go to the next problem, next question in here. Machine programs and data that are processed on this processor are shared in a memory with 1,024 locations. How many bits of address are needed to access all the locations in this memory? Don't answer the question, because if you do, everybody will have your answer. So what all that is saying is that in order to represent some 1,024 locations, you need to have some number of bits. You figure that, at the top of your head, and that's your answer. All right, so we answered already A and B, okay?
So I have a quick question about that.
All right.
So when you say 1024 locations in memory, are there, because like I know when we were going over VESP, you're using 000 for A and then 001 for B. So do those 1024 locations include like A and B and anything else?
Those are hexadecimal digits, Gabe.
Right.
The ones you gave.
Right. So I'm saying for VESP, you had those locations built in. Are those locations included in those 1024 options?
Let me just read the question one more time, and I'm going to ask the question this time to you. Machine programs and data that are processed on this processor are stored in a memory with 1,024 locations. How many locations?
1024, I got it.
Okay, 1,024 locations. Again, how many locations? 1,024. Is it 1,025? No. Is it 1,023? No. Is it 2,048? No. It is 1,024 locations. And you need some number of bits to represent each and every one of these locations. You want to represent, location 0, location 1, location 2, location 3, location 4, location 5. You know where it's going to go up to. Location 1,023. How many bits do you need to do this is the question. That's all it is.
Got it. Thank you.
You're welcome. All right, let's move on now. We just answered, by the way, there's a mistake in there. I think this should have been D here. I'll fix that right here. You can fix it on your homework set. And everything else will be, it'll just be E and so on. All right, now let's continue. I just want to make sure that, you don't make something simple complicated in your mind. I really want to insist on that one. Just keep it to the question and don't, I like the fact that your mind wanders and then tries to go to places, but keep it on the prize.
Professor, we can't see your Word document. Not a huge deal this time.
Yes, yeah, I don't think you need to see it. I'm
Okay.
just changing these, letters, and I think I right now I just want to say, share with you. If I were to write something, I want to write it on my iPad is what I'm trying to do. I think you probably have a copy of this somewhere. I hope you do. You want me to share it with you?
I mean, I don't need it, but I was just like, I didn't know if you wanted us to see it or
No,
not.
no, I'm reading the questions. I think, most all of you should have this somewhere, that you should be able to see this. I just did the first three parts, A, B, C. Now I'm going to go to D, which is a little more involved. The reason I'm just, like trying to get some speed here because I want to do something else also today. So, and this way, we kind of like got the first part, three parts of the problem pretty much done. So you don't have to think about these. Now you get started and you say A, B, C, and then put these answers down. Part D, as the architect of this process, or you decide to include the following 18 instructions. So now you're being told that there will be instructions just like in VESP, you'll have some instructions and they have their mnemonics. Also there, I guess, somewhat, pseudo explicit represent descriptions. Like add means add, like take two numbers and add them. That's what add means. Subtract means subtract. But I also put these little mnemonics. So they're going to be, you can, when you, write your solutions, you can just write them in terms of like ADD capital, SUB capital, etc. Increment, decrement, and I labeled them 1, 2, 3, 4, 5, etc. Shift left by 1 bit, shift right 1 bit, and I counted them like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I counted 18 instructions. Let's see. Did you all count 18 instructions in here? Do you all have 18 instructions? Do you all read 18 instructions?
I read 18.
Yeah.
Yes.
Okay, so let's not dispute that later on. So there are 18 instructions in here, and every one of them has been sort of described. You know what shift left by 1 bit means. The only question you may have, when I shift something by 1 bit, am I going to put a 0 or a 1 on the left hand side, on the right hand side? Well, this is what's called a arithmetic shift. In fact, even in the logic shift, you will put a 0 on the right hand side. This is a shift with a 0 on the right. If this were to be a right shift, there is an instruction called shift right 1 bit. That's a right shift. Then you need a bit on the left. If this were to be a logical shift, you will put a 0. If it's an arithmetic shift, which this is, then you're going to take the bit that you just moved from the leftmost position to the right and re-enter it on the left. In other words, take the sign bit and stick it on the left. If the sign bit is 1, put a 1 on the left. If it's 0, put a 0 on the left. Okay, that's called a shift right by 1 bit in a sort of arithmetic way. That's what the right shift is. Is that clear for everybody?
Could you say that one more time?
So you're shifting something by 1 bit to the right. Everything goes 1 bit to the right. A space opens up here on the very left. I want you to take the leftmost bit of what you had before you did any shifting, stick that back into the leftmost position that's been now left, blank. Take everything 1 bit, by 1 bit to the right, and then put that bit on the very left-hand side that you had before the shift. Take that and then put it on the left. No spaces left.
Wait, sorry. So are you copying the very last bit
Let me
after
just
the
do this.
shift, or is it always a 0?
This is going to create a question I rarely realize. That's okay. Okay, let me just show this to you. Okay, give me 1 second.
Professor, can I ask a quick question?
Hold on for a second, please. I want to answer this question first. Okay, give me 1 second. Okay, so where's our class here? There. Let me just do this and I'll answer your question, Yekta. Give me 1 second, please. Or let me just do this first. Okay. So now here's our lecture number 5. I just write this so that, at least you will have some representation of what we're doing today. Okay, so there's shift left. All right, I'm going to just write some number arbitrary. Let's say just keep it simple, make it maybe 4 bits. Okay, that's my number. I want to shift it left. Okay, so this 1 disappears. I get 0, 1, 0, and that 0 goes back in, or just put a 0, even if maybe I shouldn't say this because you'll get confused if I did it. Let me just say this, okay? Don't even shift it, but put a 0 in there. All right, enter a 0. Always, always. Okay, not even think about it. All right, that's it. That's left shift now. Now the right shift. Let's just take the same number. Okay, 1, 0, 1, 0. I'm going to right shift this. This one drops out, so I get 1, 0, 1. That is a 1. I stick it back in. That's called the right shift. Arithmetic right shift. Now, just to do another example, so you understand this. Okay, here's another example. 0, 1, 1, 1. I shift it by 1 bit to the right. This goes away. 1, 1, 0. Push it back in. All right, everybody, is this clear for everyone? I don't think there's any ambiguity here. Okay, now let's go to Yekta's question.
When remember how we draw the fetch, the 4 flip-flops for fetch and then connect it to the decoder.
Right.
So the decoder outputs are the instructions that we have, like the 18 instructions.
8 instructions, right? They had their, so you put those 3 bits on the left and you get basically something hot on the right, one of those outputs.
So I wanted to know for the fetch process for the 4.
We're not there yet. We're not there yet. We're going to get to all those things.
Okay, I just wanted to know, how we said how MAR equals PC and then PC equals.
Yeah, we're not there yet. We're not even thinking about that yet. We're going to look at those cases.
Okay.
So first, let's just know that we have 8 instructions. I'm just trying to describe you what these instructions are like. There could be some ambiguity as to what this instruction could mean. I just try to explain that. Let's go back now, and you will not see this on your screen, but I'll see it on mine. I want to get back and I want to continue from where I, left off. All right, so here it says, give a table of opcodes for these 18 instructions and show the instruction format specifying the opcode, an address, and operand fields, if any. If there's any one of those fields, specify them, okay? For each instruction. So now you're going to do your instruction, basically. Now think back to our VESP machine instruction. What did we have? We had some 3 bits on the left, and everything else, it was either ignored or we used that as a 12 or 13-bit address. Okay, that's all we had, nothing else. Now here, if you go back a little bit, we had these 18 instructions, and we decided that you would need 5 bits for this, and you needed some number of bits for this, okay? Now, whether you need this in each and every case is not clear. Okay, so let's, for example, look at add instruction. All right. Now, the add instruction, has not quite been specified in here. And in order to really answer this question, you may have to look ahead and figure out if these instructions require anything other than A and B as we define. I think some question came up yesterday about this. And I'm looking at it here, I notice that you don't see this, but I see it in front of me. We're not actually referring to more than 2 registers. We only have 2 registers to speak of, okay? A and B, they are the only 2, just like in our VESP. I think originally I might have had 4 registers, now I've just reduced them down to 2, okay? So I'm just reading part E, see if you actually depend on that somehow. Okay, so I think that being the case, the fact that we have only 2 registers, you don't actually need in part D anything other than the opcodes, and if need be, an address or operand field, but it seems like you would probably not need the operand field to begin with. Okay. Now, so you're now looking at a 5-bit of opcode, and let's call it 10-bit of address field. Okay, so that will bring you up to 15 bits. Does that add up for everybody? Maria, does it add up for you? 10 bits of address, 5 bits of opcode gives you 15 bits.
Total. Yeah, that makes sense.
Okay, good. And so you can choose those opcodes you like. You could actually go in the very order that I've given you these. You can put, 0, 0, 0 for, 5 zeros for add, and then maybe 4 zeros followed by 1 for sub, etc. You can go kind of like in that direction. Okay. So I think you could go ahead and do this. Part D is not that complicated.
Wait, Professor, can I ask some questions about part D?
Yeah, by the way, this is part D. It was written as part C in the problem. Just change it to part D. Yes, what's the question?
So the first one is that, are we only going to have one, like, because in some of the examples you did earlier for VESP, right, you would first have an opcode and an operand section with the remaining bits, right? But then you would also use the subsequent like word of like the full total number of bits also for like an operation. Is that something that's going
Yes,
to be-
like it's the second group of 16 bits.
Yes.
Well, that will come up, I guess, when you're doing the load and the move instructions.
But for the other ones, it's going to only be like one.
Well, you check it out for your own benefit, right?
Okay. And
Complement, logical or, logical and. Think about those.
so for all of those, my other question was that for all of like the operations, right, like the logical and the new addition, subtraction, can we only add and subtract the 2 registers we have, or are we allowed an input like from the user?
Well, not from what I could see here,
So if we
because
can
it said the processor operates on operands in 2 registers A and B. There's nothing else.
Okay, thank you.
Yeah,
And
there's
then-
the answer to your question.
And then one last question about this part, because I was thinking about this for a long time. Did you want us to draw it out like how you drew it out in lecture, or can we just mention that it has these
Do it
parts?
like I did it in the lecture so that you won't get penalized.
Okay, thank you.
Okay, all right. So I think part D has been answered. By the way, I just sort of skipped part C when I was doing part D, but part C gives you the hint that you need a bit to separate A from B. So now altogether you have 16 bits, a bit for identifying A or separating A from B, and then 5 bits to identify the opcode. That's a total of 6 bits. And then you have 1,024 locations. So you can see that this was carefully crafted up until now. In other words, we have 16-bit words that will represent the first chunk of our instructions. In the case of load and move, you're going to go to the next 16. So again, you can organize this memory like, okay, here's 16 this way, 16 that way, and then all the way down to this way, 1,024 locations. Some sort of a rectangle, right? All right, so this is the way that you're sorry about this. You can see my screen. I assume you do, right? I think you do. There it is. So you're looking at this sort of RAM thing. Okay. So like this way it is 16. And this way it's 1,024. And your instruction kind of looks like this. I think we kind of answered most of the questions here, as you noticed. Okay. So you can actually put the 5 bits here. You can put an extra bit here. And then you have 10 more bits. 16. You get the drift of this. I think you understand what we're doing here. All right, let's go back to the question. I want to make sure that you get this homework completed and you have no excuse to say that I had 3, 4 more homework problem assignments and I couldn't do this because of that. Just don't do that. It's a bad precedent for everybody. The first homework, you have to get it in time. I don't want you to, look for an excuse unless God forbid something happened to you or to your family. Understandable. But besides that, I had too much work to do. I had other homework assignments to do. Just don't do that, please, because I think it's going to slow everybody down. That's why I'm taking the time to explain most everything to you here. And then once you get to the habit of doing this on time, I'll still give you some input, some feedback, some help with everything. But I want you to basically, like a car, get started by yourself at some point in time. Okay, let's see, where was I? I was just doing the go back to the this particular thing. All right, so now something that I didn't quite explain or explicitly mentioned in class, but I think it's obvious from our discussion, and that's so-called the one hot D flip-flop controller. That one hot means that you have only one flip-flop turn on at any point in time. That's why we call it a one hot design. There are other alternatives to controller design where you actually compress the total number of states by doing this log reduction, so that you have to use a decoder to actually know exactly what state you're in. In this case, we don't do that. We have one flip-flop for each event that happens in our computer in terms of these steps that I explained to you, like copying something from one place to another, or adding two numbers. All those things are done separately and individually in their own times. This will also be the case when a vertical, for example, sequencer is designed, but those states, those not states, but those situations would be actually coded, compressed by using fewer flip-flops, fewer in the sense that you're going to take the total number of states, take the logarithm, base 2 logarithm of that, and then you need that many flip-flop states, but no more. So this is an expensive design, but it's also a simpler design because you can actually, by tracking where that flip-flop, where that clock shows up, where that one shows up at the Q outputs of one of those flip-flops, you would know exactly where you are. Simple design called one hot design. So provide a one hot design, right? The first 3 steps will be the same. Fetch, decode, execute, nothing changed here. Okay. You'll fetch the instruction and then you'll come up to the decode stage. So the fetch would be like, put the PC into MAR, go and read the instruction into MDR, take it from there and put it into IR. Those 3 steps are taken care of. You don't have to think about this 3 times. Just simply write these things, one after the other, put them down here. Okay. Just write these arrows like so. Just say MAR is equal to PC, and then say, MDR is equal to MEM, MAR, and then read is equal to 1. And here say IR, here say IR is equal to MAR, and you're done, right? We call this, I assume, Q, flip-flop rather. Flip-flop 1. This doesn't change in your assignment. You got the first 3 steps already taken care of. That's your flip-flop design.
Isn't it IR equals MDR?
MDR. Thank you. Thank you. I
Okay.
think you're following this pretty well, Ekta. Congratulations.
I'm trying. And my question that I was trying to ask earlier was that this process of MAR equals PC, read 1, and IR equals MDR, that's always the same for fetch for any
I'm sorry, hold on.
circuit?
Yeah, this is the same for this particular machine or these kinds of machines. Let me just do this also. Somewhere in there, you have to increment program counter. All right, so you get the idea, okay? And so the first 3 steps are obvious. Now, what do you do after this? Okay, so when you get up here, you need a decoder, but this time you have 18 instructions. So we had a 3 by 8 decoder, but this time we're going to need we can actually do either 5 or 6 because, you know, but that's just better to do 5 here. And we use that bit that I just defined for something else. Okay, so these are the 5 bits. And how many outputs will you have here?
32.
Okay, all right. You're going to use only the first 18. Remaining 14 will go unused. Don't even touch them. Just let them alone. Leave them alone. Okay, so most likely this will be your add instruction. This will be your sub instruction. Okay, just not, you get the idea. I think you're beginning to see the picture more completely.
Professor, do we not need a decode and execution flip-flop after the fetch?
Yeah, to get it here. Okay, so you need a clock cycle for this to actually, you know, mature. You're right. So if this is, I don't know what I call this, A maybe, or is it like, what did I call this?
Last time you called it C.
C. Was it Z?
No, it was C.
C, okay. So you take that C and then you basically you get the idea, correct? You know how to do this, just like in VESP. I don't want to draw the complete diagram for you.
But so you want us to draw out like that gate level
Yes,
logic
draw-
for
exactly.
every 18?
Just do all these things, yes.
Okay, got it.
Do all these things that I'm just drawing for you. Now you have to go to work, okay? Now you know that your LDA and your move steps will be the same because nothing changed in that regard. Isn't that true? Right, everybody? Nothing changed in there. Load and the move instructions are the same. Halt instruction is the same. Jump if 0, jump PS. Jump negative is a little different, but the others are the same. Okay, complement is the same. Now, when it comes to A and B, there is a statement in there that says, and a clear also. Here it is. It says, on the A or B register as identified by the 1-bit register select field in the instruction. So in other words, what you're jumping with, remember, we always jumped with A being 0 or A being negative or A being positive, etc. But it says that you're going to have to now take into account this bit right there. You have to check that bit to see if you have to jump on A or jump on B, being 0 or positive or negative. You have to involve that bit. If you don't involve that bit, then your answer will be wrong. Also, it says clear instruction clears A or B register as identified by the 1-bit register select field. So when you have that clear instruction opcode, you have to clear either A or B, and the one that you clear is actually stated by this, I guess 0 for A and 1 for B. You got to do that, okay?
Quick question about the
Again, also, look, you can see that some of these instructions can store the result in either A or B. So you have to pick the destination the same way you pick which register to clear, which register to complement, or which register to jump with, all those things. The same thing applies for add and sub and IOR, all these other instructions. Does that make sense? Just get creative about using this 1-bit, right? We put it in there, so figure out how to do it. That's what it is. Try to find out what to do with that bit. Now that we put it in there, you should do something about it. Everybody clear on this one? Why did we put that bit in there? Like for no reason? Just to leave it there? No. We put it in there because we want to use it. And how do you want to use it? Either you have to sort of like take this stuff out of A and clear it, or complement it, or increment it, or decrement it, or when you take two of them, like add A and B, where do you want to put it? Into A or B? That's what that bit tells you.
So Professor, so for like the instructions that are like a function, right? Like add, and, or whatever, right? We are passing three locations, right? One for one argument, one for another argument, and one where it will be stored.
Yeah.
Okay.
And there's no choice into, like when you're adding two things, there's no choice. You have to add an A and B. But where that goes, there is a choice. It could either go to A or go to B. That's where that bit comes in. So you have to invoke that bit every single time you're going to do an operation, and either the source of the operation, as in the case of clear or complement or increment or decrement, shift left, shift right. In those cases, you have to figure out which of those two registers you want to shift left, right, increment, decrement, complement, etc. When you have an add instruction or an OR instruction or an XOR instruction, those instructions, a sub instruction, etc., you need to specify where you go. Let's say you OR two, both of them, A and B, were exclusive OR or just OR. Where would you put it? Into A or B? You have to decide. That's what that bit tells you. I don't think there's any ambiguity about this. Okay, everybody? Are you all clear about this bit, what it does? Is that clear for everyone? Any ambiguities? Any questions?
I have a question about the jump bit, like the flags.
I just said that, right?
Well, I
If
mean,
you're
like,
jumping, you either jump with A or jump it with B. In other words, A is 0, you jump. B is 0, you jump.
so do we just like, do we write like ZA? Because before we just wrote like Z for the 0 flag.
Yeah, you have to now figure out that there must be a 0 flag for A and a 0 flag for B.
So there is two? Okay, thank you.
You're welcome. All right, I think that's fairly clear. Let's just continue now. Determine the number of clock cycles it'll take to fetch, decode, and execute each instruction. So you're going to have a table, and you're going to say add at the top, and you will say how many clock cycles it'll take. You'll just count the number of clock cycles, just like I did. And don't ever forget that last circle that I took into account when I came back to the very beginning. I said I have to allow myself a clock cycle for the result to occur through that first flip-flop on the left. So don't ignore the count of that transition from the last place you're going to get at back to the output of the first flip-flop that starts everything at the beginning, which is to say this flip-flop right there. So allow this time, one clock cycle, and add that to the total. Otherwise, you will be computing it wrong. Don't forget to add that last transition. And I emphasize this in class several times. So that's not that hard. Problem F. Okay. That's actually now, it's going to be, yeah, I actually changed it. Yeah, that now is F. Again, fix the two C's, you'll get the right, right parts. And then I guess I must have fixed all of mine here. So the next one is G, which says, show the design of a typical flip-flop in register A and the MAR. Okay, we didn't do it yet, so I'm going to do that today. Not for this problem, but for VESP itself. And you will find out how to do this when it comes to the A register and then the MAR in this problem set, set, okay? All right, so then the rest of it's somewhat, up to you, right? I mean, you want to really ace this homework, you want to make sure that you get those two parts done as well. What is it? If you could add 4 more instructions to this processor's repertoire, Which instructions would you choose? Explain your choices. Why did you put those in? There must be a good reason for you to add those in there. And then it says modify the controller in part D so that it can execute the instructions you choose in part G as well. Okay. That means you're going to have to look at these 14 places and add some more logic into those, like you have to have 4 more. That means now you're up to 22. So take advantage of those left alone. You don't have to change your decoder. There's space in there. Just stick some more instructions in there. And then, explain why you decided to put those 4 instructions in there. What benefit did you draw from them? Now, if you, for example, you make all 4 instructions identical, that means you're cutting corners. That means, you don't want to do the work required. And you'll probably be penalized for that. I mean, you may be smart enough to say, hey, I chose the same instruction 4 times. That will not be welcome. Okay. So you have to create some 4 instructions and you really have to justify what they are. I don't think you have to kill yourself to make a very complex instruction, but whatever instructions you choose to put in, you really have to be able to justify them. All right. I think I spent enough time on all aspects of this homework problem. You probably feel 100% better now. Isn't that true, everybody? Or is it not true? That it would have been better if I didn't tell you all these things. Which?
I feel better.
Absolutely better.
Yeah, thank you so much.
Okay, but I just want to know, because next time, if it didn't make a difference, I will not do this. I just want to poll everybody too, so I know that that's
No,
how you think.
it certainly helped. Thank you.
All right, you're welcome. All right, very good. Now, so let's talk about this one case, which is really one of the things that I did not get to complete last time. I want to tell you about this typical flip-flop business. This is like very critical. Everything that we've done so far, pertain to the controller's sort of control signals, all those arrows that we drew. We never really acted on those. We just left them there, kind of dangling, but we wanted to make sure that those arrows go somewhere and then actually they do something. So whatever we wrote at the top of those, like in this case, okay, whatever we did, on those, like PC, like right there. Like that thing there. Let me just actually close this so I don't have to, yeah, right there. So that is an action. That's like an arrow here. Okay. That's something we have to do. What that says that when I get to be here, when the pulse shows up right there, which is that signal, I must now copy PC into MAR. So what that means is this, basically. I got 2 registers. One is called PC, the other one is called MAR. So here's how they look. So this data path design is what we're doing now. Part of our as well as transitions between control registers like the PC, IR, etc. and MAR, right? Like the one I just showed you, which I will explain now. Okay. This is what we're doing now. We're basically focusing on this. So here's that PC to MAR business. Here's what we have. Something very simple. How many bits do we have in this PC? How many bits in total?
The one that we were talking about in the homework?
No, in VESP, we use 16 bits, right? This is the program counter's width. And that's PC. And we want this to go to where? At that point in time? Into MAR. Okay, we don't shuffle these flip-flops as we map them. We take this flip-flop's output to that flip-flop's input, this flip-flop's output to that flip-flop's input, and so on. Okay, this is called transfer. And it's actually parallel transfer. So there's a typical flip-flop here, you know, whatever you want to call this. Maybe here's a typical flip-flop. Here's a typical flip-flop. And here's a typical flip-flop. These are corresponding to each other. This flip-flop has an output, QI. Okay, and this flip-flop has an input called DI. So I'm just going to open these up. I'm going to sort of like, you know, remove them from wherever they are, put them into some separate location here. So we have this, you know, I call that QI maybe QI of PC, okay, because it's coming from the PC. Here's the QI of PC. And that's supposed to go to DI of MAR. So something from QI will come in here. So this is a typical flip-flop. This is also a typical flip-flop. So instead of showing, you know, the entire diagram, I'm going to only focus on these two typical flip-flops. Whatever I do with these two typical flip-flops, you take the same thing that I do here and then replicate it inside this and this, that and this, and then this and this. In other words, copy this stuff that I create and paste it into each and every one of them. Whatever happens with these two flip-flops will happen with all the other pairs. So this is why I call it a typical flip-flop. So what do I call this, Maria? Maria, just
A
this
typical flip-flop.
big flip-flop. Typical, yeah. Don't forget now. It's a critical word. Typical flip-flop. You will remember this at least until the end of the semester and maybe in the final exam as well. Typical flip-flop. So now let's think about what I have to do here. Let's just actually keep it there. Now think back to all the times, all the sort of like situations in the controller design that I had where I had to bring something into MAR. Let's actually go back and take a look. Look at our individual steps. Let's look at our, you know, controller design. All right. Now I see there, for example, that something is going into MAR. That's a step where I have to put something into MAR. I see here a step where something goes into MAR. Okay. I see something here, maybe earlier, like the first place, I think, or not even there, but here something goes into MAR. Something goes into MAR. Okay. So you see lots of places, and this is the one that we're actually doing here. Something goes into MAR. So there are many places, where something gets into MAR. What goes into MAR is determined by the very clock, by the very place, the time, instant, where we made that decision to push something into MAR. So you can see that MAR is not going to be just fed from PC. It may also be fed, as you can see in, for example, here, down here, as we were just looking at it. Let's see, right there, it could be fed from IR. Okay. Instruction register. It can even be fed from, as we saw later, it can actually be fed from MDR. So there are potentially 3 places that AR can receive an input. If you have a choice of several things going into one thing, what kind of a gate would you think of using?
OR gate.
OR gate. There you go. So that means when we're thinking about this, we have to put stick an OR gate in front of it. Okay, there's also a clock input here. So now one of those inputs, as we determined, is actually nothing but PC and the particular typical flip-flop output, which is this output here. But we don't do this all the time. We do this copying of PC into MAR when we happen to be in here. Right there. That means when Q1 is equal to 1. And nowhere else do we actually move PC into MAR. That's the only place that PC goes into MAR. And if you search through all of the things that we've done in terms of the sequencer itself, like from this diagram all the way to the end of it, you will not see any other place where PC goes into MAR. That means we should do this when that arrow, MAR equals 1, goes to 1, which really is synonymous with, if you just look carefully, with that wire or that output Q1. So all we have to do is to go down here okay, go down here and then say end this with Q1 and then push this in here. So what we did, we copied that ith bit of PC to the ith flip-flop of MAR, and we did that copying when we had to do it, and that's when Q1 is equal to 1. This, by the way, is the same signal called MAR is equal to PC. Same thing, that little arrow that we had over there. So that's just to put that in. There are, other things that we have to do. One of them is going to get that IR into MAR. The other one will get MDR onto. We're not doing that here. If I were to do this, I would go back to the sequencer. I will figure out exactly IR goes into PC. I will figure out exactly when MDR goes into PC. I'll determine those. Let's just look at the IR case, for example. So when does IR go to PC? Let's take a look. Okay. Here's one. Okay, so I have to do that. In other words, I must be at state C, right there, and I must have a jump or a JEZ or a JPOS, which is basically this wire right there, which I think, I call W. Okay, so W is the wire, is the signal I have to pick up and do my IR moving into PC. That's one place. Is there any other place? I guess the answer is most likely yes, but let's figure this out. There it is, right there, when I'm at step D. I'm copying IR 3 through 15 into MAR. Actually, that's going into MAR. That means I have to put this on the front end. That is, MAR's bits will change now, not with PC, but with IR, just like the other example. So I have to take D or W. Anything else that we see here? We should also do that. I think that's it. There could be actually one other place. D is 1, W for sure is 1. And I think in the case that we are doing the move instruction, there should also be 1 there. There it is. So take H, take W, and take D. I think it was D here. Or those signals together. Okay, so this one will be like this. Was it D, H, and W, correct? Is that what I read? Push it in. And what is the other one? This one is? Another AND gate. This is a typical flip-flop, by the way. And this would be MDR, typical flip-flop. And there will be conditions that I will leave you to figure out. Leave it to you to figure out. All right, now this is really the D input. There's also the clock input, which I have to pay attention to. Let me just clean this up so that, it's a little bit better organized, okay? I wrote a lot of stuff in there.
Professor?
Yes, sir.
I have a question in regard to PC or MAR equals PC. Don't you also have the MAR getting set to the contents of PC when you're doing the load instruction at point B?
I used that, did I not?
Well, so I think we maybe discussed it, but then didn't write it on the diagram. So that would just then be like also a Q3 option.
Yeah, let me take a look at this. If I omitted it, I would, yeah, let me just do that in just a second.
Okay, thanks.
I know what you're asking, okay. So basically there are 3 things that things can come from for this thing called PC. These are all typical flip-flops coming from different registers. Okay. And there's this one flip-flop into which these things will go. So here's that one flip-flop here. And it's got this input DI, and this is the flip-flop for PC. Okay. And we put an OR gate in front of this. It's got 3 things coming into it. Now, one we said, I just did PC. Let's see. Is this what you were asking? Was that Gabe? Who was that?
Yeah.
Gabe. So you asked this question, like you were saying, wouldn't we get this PC? Oh, by the way, this is not PC. This is MAR. You were asking whether we actually did something brought this PC some other place. Let's see. Let's go and find this. I said that it'll come definitely at the very beginning, which was actually Q1. Okay. By the way, that Q1 has nothing to do with this PC Q1. Or this is typical QI. Let's see. Where was it? I think I kind of remember we copied something into MAR from PC, correct? Some other place. Right there, maybe not there. Certainly not here. Where was that? I kind of remember it would have been.
I think it was that point B right there.
Point D?
B.
B as in boy?
B as in boy. Yeah, it's right. It's on your, it was just on your screen. You just scrolled up, but it was there.
Okay, here's B.
And then if you go down a little bit more, right there.
There you go. There you go. Okay, so there's this place, which is actually the place where, we're at B. So that means this. Okay, you're absolutely correct about that. That's also a place where we copy PC into MAR. I hope that that's the last of places. If you find any other, you have to stick it in here. Okay, so what that means is now that the thing that will come from PC, which is this place, okay, will have to be ended with two things. One is, I call it Q1, and the other one is B. Okay, they have to be both. Sorry, not that way. I'm just feeling a little bit out of space here all the time. There we go. Q1, B, one or the other. And then this guy here goes like this. Okay, everybody? Does this make sense, Gabe?
Yep, that's perfect.
Okay, good. Now there's a clock input, which I will just, come to in just a second, but let's just finish this now. What did I say about IR? When does it come into, MAR? We said there will be how many places here? Some DH and W, correct? Assuming that's the case, that means we have an AND gate here. And one of the inputs of this AND gate will be this. But the other one will be this OR gate's output, which is going to be those three signals, which we talked about, DH and W. Okay, that's that. Now, the only other thing is MDR. I don't know when we copy. I think that's only when we have a move instruction, correct? Do we ever copy? Maybe we do copy it into, when do we copy that? We're talking about going into MAR. Yeah, right there. So that will be like Q6 or G, point G. Do you know of any other place, anybody, where we copy MDR into MAR? I don't think we would. Okay, so go down here. Go down here. And then the only thing that we have to do now is to take this guy and it with G. These are all marked in the circuit that we drew before. That's that being this place here, G here. Right there. This place. That is when MAR needs to get something from MDR, okay? And of course, this case, these are and this one is so those three cases, each of which, each of those three cases can actually push something into MAR. Exactly what time? Well, exactly when these, auxiliary conditions happen. So what I need to do is to get my clock input and end it with, here's the clock. And I have to feed into this one of these cases, okay? Which will be, basically, if I were to draw this separately, I should either be in, it's like a big OR gate. Okay, like this would be Q1, B1, and then, D. I can draw maybe an OR gate, but I'll just, write these down. H, W, and G. And also QI. Q1, that is, I'm actually, wait a minute, Q1, I wrote this Q1 already. This is it, there's no more. That's it. Q1 or B1 or B, not 1. DHW and G or G. Each of these signals can actually trigger a copy, but no other copy process from one of these registers into the MAR's typical flip-flop. Typical flip-flop also here. So I basically explained to you in the case of VESP how this kind of works as far as, defining these so-called typical flip-flops, DI inputs, in terms of the QI outputs of the representative flip-flops. Not everything will require this. In other words, in some cases, you may just have one of the registers go into, output-wise, QI-wise, into one of the typical flip-flops DI inputs. Now, there's one other thing maybe I should mention this, and we'll call this a class. When I'm doing sum, remember, one of the things we did was, so another typical flip-flop case is what goes into A. Now, if you remember, we only have 2 instructions. We're not going to do the other ones, like the load and move. You can actually target A either from a load or a move instruction, but we're not going to write this here. So the possible sources for DI, typical flip-flop input for A are complemented QI output of that same flip-flop, or the sum of the QI outputs of the typical flip-flops QI of A and QI of B. Okay. So-
Professor, could you scroll up a bit, please?
Yeah. Complement is not that complicated, but the sum is going to require that we actually add some two 16-bit numbers and then generate the sum bit. Okay, so we need to get the sum bits generated here. What that means is now we have to, remember from ENEE350 sum material. So the sum of QIA and QIB is generated by an adder circuit. Right, you all remember, I'm sure, that you had something like a carry generation, first of all. CI, this is carry, is equal to GI plus PI times, CI minus 1, where GI is equal to AI and BI, and then PI is equal to AI exclusive or BI. This is called carry generate. This is called carry propagate. Bits. Okay. And you use these two, bits, sets of bits, there'll be exactly 16 of these to generate the CI. When you generate the CI, then you have the sum bit, which is equal to AI exclusive or BI exclusive or CI. That's how you get these sum bits. Assuming that you have these bits ready, then if you now look at the typical flip-flop of A and B, you will see this. Sorry about this. You will have this basically. Now I'm looking at two flip-flops. This is DI input. This is QI output. This is A. And this is B. DI input and QI output. This is sort of like that QI is like AI. And this is like BI. And we have to basically think of this as like exclusive OR together. And this will be exclusive ORed with CI. This is like AI, BI. Okay. And that will then be, this is the exclusive OR gate. Okay. And that thing is the sum bit, which will go to back into here. But we need a OR gate in front of this. Let me just actually put this DI here. That's the same place. There will be two possible inputs here. One of them comes from the complement of A. The other one comes from the sum. So wherever the sum is, I'm going to put the sum into A. Where the complement is, I'm going to put the complement bitwise. Okay, I'm going to take that same flip-flops just so that, we have it a little bit this way. I copied it down here. Okay, I'm going to draw this now. Let's call this the sum bit SI. Okay, that SI now is going to come in to the same flip-flop. So here's the complement case. I will do this. This is AI not with a control input. And this is SI with a control input. Okay, so what is the control input for, complement? Sum. Let's take a look at these signals. Outputs of the decoder will tell us exactly which is which. Okay, I actually give them only one name. Let's just go back here a little bit. There we go. Did I give this a name? Complement and add is all I call them. I didn't actually give them particular names. I just call them add and complement. Okay, that means that add command and the complement command is all I said for these two arrows, as you can see it right there and right there. So I'm going to say them, I'm going to just use that same signal sort of representation. Okay, so I'm going to call this right here. This is complement command wire that I just showed you there. And this is the add command wire. Okay, and that's how they go in. And of course, my clock will be ended with the clock here. And I have to have an OR gate. This would be like add command. And this would be complement command. Okay. That actually brings us to the end of the class today. Everybody, I think we learned a couple of new things today. I assume we did. I certainly did learn a few things myself by actually relearning. I relearned what I knew, which is always good. It's like refreshing a RAM memory. Okay. And you can see that you also came along and learned with me, right? You understood something. Some things may have been left a little bit fuzzy here for you because I kind of like rushed my design, but you get the general idea that the clock participates and also the D input participates. And the issue is typical flip-flop idea. We got to get those typical flip-flops in front of us, and then the wiring is almost like forced upon us because we understand that this is all about timing. We want to time things so that whatever we put into wherever happens at the very time that we desired. And for this, we use all the material that you learned in ENEE350 so that, that knowledge is beneficial. And now you actually understand why they taught you all those things that you learned. Because with those, you can represent just about any controller, describe it. Okay, the other thing I want to mention to you, I think I did upload my lecture notes, in other words, the things that I've been scribbling here into Elms. I think it's under something 2001, like lecture notes 2021, I'm sorry. And if you dig into that folder, you're going to be able to see exact replica of everything that I've done prior to this class. And you can kind of like, go through those and then compare your note taking with, whatever I wrote down on the actual iPad of mine here. Was this location acceptable to everybody? My lecturing wise, or would you prefer the other one? One advantage that you get here is that I got this beautiful instrument in front of me. You probably might have seen something like this, right? And I play this sometimes here. about that, huh? It's a nice place. So if we stay here, maybe once in a while I'll get inspired and I'll play, a little piece of music for you. All right. So this is my music corner. I got about 5 or 6 of these lutes, they call them. There's a smaller one in here, a tinier. There's a big one there, big one behind there. And then there's another one over there. And I have another instrument called oud. So when I actually don't teach and don't do other things, I come down here and I record music. I got these nice microphones. 2 of them right there in front of me. You can see.
You also sing?
I also sang, but not today. At some point in time, I'll sing. But I got all my instruments here. I got a drum also, which I just moved away from here. Sometimes I dump, drum over other things because I'm using something called Pro Logic, a Logic Pro, that is some Apple product, which gives you the ability to basically, play over or record over. I could do several runs and then create some, music that sounds like played by maybe like 24 people.
Do you upload them on YouTube or anywhere?
I use them. I put them on SoundCloud. On SoundCloud is where I, not on YouTube. No, I may have had 1 or 2 on YouTube, but mostly I put them on SoundCloud. All right, so we're gonna have a lot of ENEE350 and maybe once in a while some piece of music. So get ready and then buckle up, as they say. And I come Thursday, I'm going to talk about the programming. We'll get into some programs now. I think the hardware side of things pretty much have been done with. We understand this. We're not going to replicate this for the next computer like the 16-bit edition or the other ones. This was just like to understand, how we actually build something into a piece of, flip-flops and a set of flip-flops and other things. But I'm not going to repeat the same thing, over and over again for the next architecture.
Professor, so what we covered today was how you built VESP.
That's right. That's right. So if I go back to that last piece, which is like the part G, the new part G. I don't know what it was before. I guess it would have been probably part F. That would, that says the typical flip-flop in register A and the MAR, right? Those are, that you have to do now on your own for the other thing, for the homework assignment, that is.
Professor,
All right, everybody.
do you have time for a quick question?
Yes, I do have time for a quick question.
So when we were writing the input to the typical D flip-flop or typical flip-flop for the MAR, in reference to the IR, when that kind of triggers it, we mentioned at location W, but I'm looking back on our diagram and I can't find on location W where we write the contents of the IR to the MAR.
Hold on. I'm just looking at do you see this? You see it, right? I can see that you do.
Yeah, I can.
Let's see. I did see that W. Maybe I was mistaken there. So you should have corrected me earlier. That now that I can fix it on this, but yeah.
Well, I see that the program counter is written to, or the IR is written to the program counter, but I don't see that for.
Where's W? First of all, let's go.
W is the end of the loop.
Oh no, but I meant some other place then. Let's just target where MAR gets stuff right from. And we were looking at IR.
Yeah, we're looking at
IR going into MAR.
Yeah, so we have D and H, which I see, but then I don't see anywhere else.
Okay, so let's see. We are now looking to see when, in fact, IR goes to. Okay, so IR basically, I don't see it here. Okay, there's one place where D is going, D tells us that this happens, as you can see it there, right? Right there. Right there, basically, you see that, that's D. And then there's other places like here, H, and we wrote those, correct?
Yeah, those two we got, and then also W, but I couldn't. That was the one I couldn't
That's
find.
where that is. Oh, is this the end of it? I don't know why I wrote W here. Let's see, that would be, that's D. That's just like to copy. We got to get that address. I think it's only 2 then. Yeah. I don't know why I wrote that W. I must have, something must have hit me here. IR. No, we're looking for MAR going and getting something. Yeah, I think you may be right. Yeah, if that's
Okay,
not
got
there,
it.
all we have to do is just, yeah, if, you know, I think I agree with you. I didn't see it. So I think it'd be safe to do this. Let me just go.
Okay.
Yeah, safe to do this. Where did I do that earlier? Earlier here. There we go. I just erased that. That should be it. And then of course that also. Does that answer your question, Gabe?
Yep, it does. Thank you.
Yeah, I think you were right about it. And so I just removed it. All right, so I think we're going to see everybody on Thursday. You have a question?
I have a quick question. So, so regarding the recording, I think you mentioned it was recorded somewhere else. It's not on the Zoom anymore.
Yeah.
I was just wondering where was it? Could you say it again? Because I can't find my Fridays.
Actually, it's called Panopto. Panopto. I think they call it Panopto.
Could you spell it?
Yeah, it's PANOPTO.
I see your recording.
You see it, yeah, but you probably logged into you can log into Panopto. But I think Xiaomin, the issue was that, as I explained this, that I think there was Zoom and Maryland probably couldn't settle a iCloud recording contract, so they switched everything to Panopto. But Zoom, I think, kindly agreed to create the links and then pass the thing to I guess Panopto, which I think is something that University of Maryland has a big contract with. So I hope, can you find it? Do you think you can log in there and then see my lectures or something?
I'll try, because I can't find my recording for my recitation. So
I think I saw yours there.
Oh, really?
Yeah, yours was there too.
So I don't think there's a specific like software that you need to log in. You just have to go to Elms and then where the options are.
Oh,
that's right, because that's been added. It wasn't there earlier.
okay.
Yeah, you're right. Exactly. It's on Elms. Now it actually shows up there. It didn't show up there because they asked me to actually activate it. But then when I went there to activate it, there's something called Panopto recording versus, Panopto impressions or something. And the other one was not activatable. And then I had to get somebody from the IT office, to actually do it manually, because they thought that I could do it. Or other professors can do it, but we couldn't do it. They had actually locked that and we couldn't change it. So until that, and I couldn't have it there until they stepped in and actually put that thing on my Zoom, on my Elms, so that everybody now, apparently Yekta can see it because it's actually activated on my Elms. Anybody who's in this class can actually see it directly.
Yeah.
Right, you can see
Yeah,
it.
I can see it now. Yeah. Awesome.
Yeah, very good. Very good. All right, everybody.
right.
I think we're all set. And
Thank you.
Yeah. All right. We'll see you
All right.
on Thursday.
All right. Bye-bye.
Sir, have a good day.
You too, Yekta. I'll see you on Thursday.
Yeah.
Take it easy. I was a little rough on you, but it was not intentional.
No, you were fine.
Okay, thank you. Okay, I'll talk to you.
Okay, well.
Bye-bye. Bye-bye.